poll was conducted amongst 500 registered voters in a certain area regarding their position on a national lottery to raise revenue for the government. The results of the poll are shown in the accompanying table. So what you see there is you have percentage of voters polled. These are all percentages. The thing you have to be careful of is sometimes students want to treat percentages as numbers all the time. You can't do that. Because, for instance, if I try to do that, it's telling me that, favoring the lottery, the people who are surveyed, 130% of them favored the lottery. Well, that can't happen. It's impossible. I can't have more people favoring the lottery, especially when I see people don't favor the lottery, than the people who I actually looked at. So we have to actually use the numbers, or I have to be more careful with the percentages, because those percentages are dealing with the percentages of males. So 62% of males who were polled favor the lottery system, 32% of the males don't, and 6% have no opinion. So if you're not careful about how you treat these as numbers, it can sometimes cause issue with your accuracy of your results. So what I'm going to do for this to make my life a little easier is I'm going to construct a table here where I split it between male and female, but I also have these groups favor, do not favor, or no opinion. I could try to set up a Venn diagram for this, but I wouldn't have just one region that's going across basically the male-female areas, or or I would have or three partitions and have the inside be males and the outside be female. It's kind of hard to kind of put it with the way this is being stated, because I have a little bit too many partitions here that would be possible. So I'm just going to use the table to do the partitioning, and I'm going to use the fact that there are 500 registered voters. So again, these percentages were probably rounded off. So as I do these, I might get some numbers in here that may not make total sense. I mean, at first, the totals, 51% and 49% of the 500 would give me 255 males, 245 females. But then as I look into the other ones, if I'm letting these be number of people or number of men, number of women who answered a certain way, I'm getting decimals, which some people get alarmed about because they say that doesn't make sense. But in this kind of perspective, it does, because the percentages might have been rounded off, and as a result, I'm trying to make sure that I'm being as accurate as possible when I try to come up with some of these probabilities. But basically, all I did was I took 62% of 255, 32% of 255, and 6% of 255 to get the numbers that I have in the male row. And I did the same thing with the percentages for the female row being multiplied to the 245 to get this table filled in. With this table filled in, I can now answer it more accurately, because sometimes a lot of students, they'll think, well, these percentages are given in the problem here. But I have to be careful about seeing what these percentages are versus what it is I'm asked to do. Because some people would say, the answer to part A was this is 68%. It was a 68%. Well, that's the probability that somebody is in favor of the lottery given that they are a woman. That is not what we're looking for in Part A. In Part A, we're looking for the probability that a person is a woman given that they favor the national lottery. That's a different circumstance. But with the table, it makes it much easier, because I'm only looking at the first column, those who are in favor. There's 166.6 women, and the total in that column is 158.1 plus that 166.6. And if I carry through that calculation, it's actually more like 0.5131. So about 51.3% of women, 51% of those who are in favor are actually women. So I have to be careful, because the problem that someone being in the group, someone being a woman, given that they are in favor of this lottery, can and oftentimes will be different than somebody who's in favor of the lottery, given that they are a woman. That's what a lot of blurring of statistics happens when you see things, even especially all the political things going on this time of year. Some people will state one of these things in place of the other, and people easily get them mixed up and thinking they're the same thing. And in part B, kind of the same thing. We're looking for the probability that a person who expressed no opinion was a man. So we're looking for the probability of someone being a man given that they expressed no opinion. Again, students will look at this table and say, well, that's 6%. Well, no, that's the probability that someone expressed no opinion given that they were a male. I'm looking for the probability that someone's a male given that they expressed no opinion. Different. And as I said before, and I mentioned before, sometimes the wording of a question can certainly have a great outcome on how it's interpreted and how it's calculated, or a misinterpretation of thinking it's one thing when it was stated to be another can certainly cause the same kind of thing. So you have to be kind of careful with this. So I'd only be looking at the data from the no opinion column in my table. There are 15.3 males in that group out of whatever 15.3 plus 9.8 would be total in that group of no opinion people. And so I would have 0.6096 be that probability as compared to the 6% that I had if I stated the probability of someone having no opinion given that they were a male. Vastly different percentages. Janssen Electronics has 4 machines that produce identical components for use in its DVD players. The proportion of the components produced by each machine and the probability of a component produced by that machine being defective are shown in the table below. What is the probability that a component selected at random, and they ask you 3 questions. What's the probability that you have just a randomly selected component, from this entire lot being defective? What's the probability of it being produced by machine 1 given that it was defective? And C, what's the probability that it's produced by machine 2 given that it was a defective component? So again, be careful with the way it's wording. We're given that it's defective for B and C. We want to see what probably came from machine 1. Whereas this table would much more immediately give you information about the probability of it being defective given that it came from machine 1, given that it came from machine 2, so forth and so on. So, now as we go through this, again, students make mistakes. They thinking that this table may just give them some of the answers off right. And every once in a while you might get a rare circumstance where you might get some information on a table that just directly translates into an answer. But oftentimes you're going to have to work with it a little bit. Because one of the things that we're looking for here, we're looking for the overall probability of being defective. We're also looking for the overall, looking for the probability that it's from machine 1 if it's defective and from machine 2 if it's defective. Well, each one of these probabilities is the probability of me having a defect given that it comes from a certain machine, not the other way around, which is like what B and C is asking. Also, a lot of times people think that if you just add these probabilities together, that it's going to give me the probability of me being defective. The thing is, since these are probabilities given that I'm from a certain machine, these just adding together are not going to do it because, it's 4% out of the 15% that came from machine 1 that, I'm looking at here. So, again, it's hard to have a direct translation over from percentages, which is what these basically are. These are probabilities, but they're percentages. Going right from percentages in a table to percentages that you can make use of for direct calculation. So now, if I look at these probabilities here, these do add up to 1, which means each one of these could be representing a percentage. But at the same token, I'm not given a whole number here, so I'm going to use these percentages as numbers. I'm going to use 15, 30, 35, and 20 as, the number of numbers of components. And so the numbers I'm going to come up with when I make my Venn diagram are going to have decimals involved, but it's going to be based off of these percentages as well. Because when I construct my Venn diagram, I'm going to show my 4 partitions, and anything that's in that oval is in group D for the defects. So if I look at this, if I do 4% of 15%, I do get 0.6. If I do 2% of 30, I do get 0.6. If I do 2% of 35, I get 0.7. And again, if I do 3% of 20, I get 0.6. And those would be the number that are defective from each one of these machines. which means I would have 14.4 that are not defective for machine 1, 29.4 for machine 2, etc., etc. So now I have numbers out of 100 that I can make use of. So now, if I want to add up anything that's in this group up here to get my percentage, then I'll have it pretty easily, because basically I'm going to have 0.6 plus 0.6 plus 0.7 plus 0.6 out of 100. That's going to give me 0.025, or about 2.5%. And now when I want to find the probabilities that it came from a certain machine, given that it was defective, I now have the numbers organized in that Venn diagram to help me along with that. So when I look at the probability that a component was produced by machine 1, given that it was defective, that's going to be 0.6, because that's how many that are defective. Out of the from machine 1 that are defective, and there's 2.5, the total of all the defects together. So it's about 0.24, or about 24%. And as you can see, since I have the same number in the defective group for machine 2, it's no surprise that when I do the probability that it came from machine 2, given that it was defective, I get the same value of 0.24, or about 24%.